Hey everybody, Mr. Lake here with a new video starting our second unit, which is all about electrons and the behavior of electrons and how their behavior is different than what you've probably seen represented in the past, and also drives all of the interactions between atoms, reactivity, bonding, all that stuff. So let's get right into it. First, we're not going to talk about bonding or reactivity yet. We're just going to talk a little bit about what electrons look like and how they behave, because we've got to break down some barriers here. We got to break down some previous misconceptions. You've probably seen a depiction of an atom very similar to this before. If you've ever watched Jimmy Neutron, you've seen this because the little dot above the I in Jimmy Neutron's name in the opening credits, I think, is one of these. If you've ever watched Bill Nye and you've seen that part where everybody goes, Bill, 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 and like his head flies across the screen, and then one of these flies across the screen. Or if you've ever watched The Big Bang Theory, and anytime a scene changes in that show, this thing flies across the screen, and it's one of these. This is the most common representation of an atom in popular culture, it really in science, pretty much everywhere. And it's not entirely wrong because atoms do have a dense nucleus at the middle and they have electrons around the outside, and most of it's empty space. But there's a couple things that are wrong with this that aren't perfectly correct. First of all, they're really not to scale. If you were to draw this accurately, the nucleus would be tiny and the electrons would be even tinier and they'd be really far away. So electrons are not nearly this close to the nucleus. And also, electrons are much smaller than protons or neutrons. But really, the bigger issue is that atoms don't look like that. Atoms look a little bit more like this. They look a little bit more like a nucleus in the middle, surrounded by a bunch of electron clouds. Not electrons are not little solid planets that orbit the nucleus as if as like planets orbit the sun in our solar system. That's what a lot of people think. That's not exactly true. Electrons are more like wave clouds that surround and fill spaces around the nucleus. Let's get into it. The reason that we know that that's the case is because of work and efforts that have been done in the field of quantum mechanics, which is maybe something you've heard of before. And I am not a quantum physicist or quantum chemist. I am not a expert in quantum mechanics, but I want to cover a couple of the basic principles, especially behind as it relates to electrons, so that we can get into thinking about electrons in a more modern way. So, firstly, let's talk about the wave equation, pioneered by Louis de Broglie or Louis de Broglie. I'm not exactly sure how to say his name. And what de Broglie discovered or found evidence for or theorized is that an electron is both a particle and a wave. Now we know this about light. We know that light is both a particle, which we call a photon, and it also behaves like a wave. But it turns out that electrons do as well. In fact, everything kind of does, which is a little bit mind blowing. Like a baseball flying through the sky actually has a wavelength. But the wave nature, the apparent wave nature of something decreases as objects get more massive. So we really only can, things truly only behave like waves in an equivalently like waves and particles when they're extremely small, like a photon or an electron. So what that means is that electrons, again, don't behave like little objects orbiting around the nucleus. Instead, they're like a wave surrounding the nucleus. So it's not like this, it's more like this. If the nucleus was right in the middle of this thing, it's like the electron is a wave flying around the nucleus, and that orange line is not the path that the electron follows. That orange line is the electron. The electron is in all of those places at the same time, it is a wave surrounding the nucleus. But often it's not a perfectly circular wave like this. It's a little more globular and makes the atom look like that picture I showed you earlier. And we'll talk about the different shapes of orbitals. Building off of that wave nature of electrons, we have the Heisenberg uncertainty principle. And you may have heard of Heisenberg before. It was the name adopted, the criminal name adopted by Walter White in the show Breaking Bad, which I can't really recommend as a high school chemistry teacher, but it is a very high quality, very well made show and something that people should watch at some point. Um, Basically, the Heisenberg uncertainty principle is that you don't know where electrons are. The technical wording was it's fundamentally impossible to know the velocity and position of a particle at the same time. But what that boils down to is that we don't know where electrons are because electrons aren't in a location, right? That was the wave principle. Electrons are not in a single location. They are a wave. They are in many locations at the same time. Now, building off of that, or kind of complementing both of those ideas, was Schrodinger's idea of atomic orbitals, which is essentially that, okay, we don't know where an electron is because it's a wave and it's in many locations. However, we can kind of put a boundary around where it is. And we can say, even though we don't know where it is, it's somewhere within this boundary. Like, it's not like we just have to say, okay, well, an electron is literally everywhere in the universe at the same time. Kinda, it is. But in reality, the statistical likelihood of that being true is so incredibly low. There is a boundary where the statistical likelihood of the electron being anywhere outside that boundary is extremely, extremely low. And so, therefore, we can kind of put a boundary and say the electron is probably within this space. And we call that space an orbital. We're going to get into that. In the next video lecture, we're going to talk about orbital shapes, what they look like, and why it's important to start thinking about electrons in that way rather than as little, you know, spheres that fly around another sphere. But first, I'm going to ask you to read one of my favorite science fiction short stories. And for that, I need you to know a little bit more about quantum computing. So basically, this principle of we don't know where an electron is at any given time, that electron can also be in multiple states at the same time, right? It's not just that, oh, we can't predict it or we can't track it down. It's that that electron can literally be in a couple of different places at the same time. So if you've ever wondered if that's possible, it is. Based on quantum theory, it is possible for a particle to be in multiple states at the same time. Now, a little bit about computers, and I'm also not a computer scientist, but the way that data works in a computer, both for processing and storage, is that it's binary code. It's zeros and ones. You've probably heard that. Data is just a sequence of zeros and ones. That's the language of computers. And the way that processors and storage work is that a bit is something that can either be in a one state or a zero state. And so if you line a bunch of bits up in a row and you toggle them into a certain sequence of zeros and ones, that can store or process computer information. And the way that our computers have developed over time is that we've been able to cram more and more bits into smaller spaces. Right now, we can like have a little tiny processor card that we put in our computer, and it's got like 8 gigabytes, which is 8 million. It's a lot of bits that can all be in zeros and ones, and so we can process information really, really quickly. Well, there's this technology that is already out there. It exists. You can't buy it at Best Buy, but it exists in like it, research, very expensive research computers and things like that. Is quantum computing. And quantum computing is based off of this uncertainty of subatomic particles. A quantum computer uses quantum bits, which is a particle that can be both a 0 and the 1 and a 1 at the same time. Because just like an electron can be in multiple places at the same time, it could also be a 0 and a 1 at the same time. So this completely just shatters all of the limits that we're capable of in terms of processing, because it's not about physically cramming more and more bits into a space anymore. It's now about utilizing particles that can be zeros and ones at the same time. And that can increase our processing and our storage capabilities insanely. Theoretically, you could even get to a point where a quantum computer has infinite processing power. Because since a quantum bit can be in multiple states at the same time, technically it could be in infinite states at the same time. And it could process infinite amounts of data instantly. Now, the reality is, of course, that we are likely never to actually get there. Um, but it's a fun thing to think about. And so the short story I'm going to ask you to read, the setup is that a group of scientists has done just that. They've built a quantum computer with infinite processing capability. It can process literally an entire universe worth of data instantaneously. And the short story is just kind of about what they learn through that process. And I think that you'll enjoy it. So you will find that on Canvas. Um, Hopefully that's enough setup for it to make sense. This video has gone a little bit longer than I expected, so I'm going to stop and I'm going to let you go enjoy that. All right, take care, everybody. I'll see you in the next video.